It is a pleasure to welcome you to the 5th edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is a pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. The International Workshop on Biogeotechnics was hosted in 2024 during the 5th edition of the AGERP lecture series. The following lecture on some reflections on the art and science of geotechnical engineering was delivered by Professor Jimmy Thomas at this workshop. Professor Jimmy Thomas is a consulting engineer specializing in geotechnical engineering, geosynthetics, reinforced soil structures and pavement engineering, with about 30 years of industrial experience. He is a consultant to TechFab India Industries Limited, Mumbai, ULCCS Limited and Matter Material Testing and Amp Research Laboratory Limited, Corey Code, and Titan Environmental Containment Limited, Canada. He is also a guest professor at IIT Gandhinagar. He has worked extensively in the field of geosynthetics and reinforced soil structures and worked as a geotechnical consultant in several major infrastructure projects. He has served on technical committees of Bureau of Indian Standards and Indian Road Congress, actively participating in the formulation of codes and standards.
Good afternoon, everyone. It's a pleasure to be with you to share some of my experiences in my journey as a geotechnical engineer. Because my work has been mostly as a practicing engineer. In between, I have had brief stints with academics, mostly as a part-time adjunct professor, etc. Okay, about this presentation, this is mostly based on my personal experiences, actually, as a practicing engineer. And I have made an attempt to demonstrate that applications of basic principles are possible in routine projects. Like some of us are lucky, we get opportunity to work in very high-profile projects, applying very advanced techniques in design, construction, etc. But most of us, most of the work are on routine, day-to-day bread and butter projects, actually. But here also, it is always possible. There are challenges like in our everyday work, and it is important to apply fundamental principles. It's not that geotechnical engineering is just a collection of thumb rules or some empirical approach. Definitely, in everyday activities, we should try to apply the fundamental principles of science and engineering. So I just want to share how I became my interest in geotechnical engineering began, actually. Because my entry to civil engineering was mostly accidental, actually. But when I decided to do my master's, I was very, very sure that it has to be only in geotechnical engineering. So, when do our love or a passion for a particular subject begins, it's very difficult to answer, actually, like that. But for me, it was sort of a love at first sight. So when I was doing my undergraduate, it was Regional Engineering College, Calicut, in the state of Kerala in India. So sometimes I used to bunk the classes and go to the library. And we used to have a good library, actually. I found this book by Shubodariov, very old book. Nowadays, most of the younger generation may not be knowing about this book, actually. So I was browsing through that book. Then I found this very interesting case study, actually. So he was talking about large diameter steel storage tanks. So these are of large diameter maybe up to, say, 30-meter dia. And mostly it is founded directly on soil, actually. And these are very flexible. It can accommodate a lot of settlement. And usually it works. But in one project, one engineer, the designer, he thought, let me be a bit more cautious. Let me put a bit more conservative design. So what he did, he put a concrete slab, a reinforced concrete slab below the tank, like around, the slab was about 300 mm thick, actually. Then that tank failed. So it was a bit unusual. Like normally, if the tank is put directly on soil, nothing happens, it works. And here, one engineer, he wanted to probably make it, his design extra safe. So he provided a reinforced concrete slab below the tank. It failed actually. Then Shabodere gave a very beautiful explanation. So, like when he says, like if the tank was put directly on the soil, the steel plates are very flexible actually. So it takes a very a fish-like shapes actually. So the radius curvature is very large, like this R1. So nothing happens to and the steel plates can easily accommodate the kind of settlement profile actually. But when he puts a concrete slab, so it doesn't have the thickness to be absolutely rigid actually to settle uniformly actually. So if it was very thick, it would have been very rigid, it would have settled equally. But it's only 300 thick actually. So it cracks at various locations like A, B, C, D like that. And at that point, the steel plate also bends sharply actually. So here the radius curvature is only R2. So the plate undergoes large curvature, which in that process the plate cracks actually. Then the liquid leaks out actually like that. So somehow this explanation, like it caught my fancy, and I thought there is something to this subject. So that was how my interest was born. Then after my masters, I did my first job. Like it was actually a precast piling project. Actually. So basically, they used to have precast piles which were driven actually, and each segments which used to be about 10-meter long, and this was for a multi-story building actually. So here, the project is in a city called Kochi on the coast of the Arabian Sea. So here we have very thick deposits of soft clay, like upper maybe 10, 20 meters are very soft clay, then firm clay like that. Then at a depth of about 40 to 60 meters below ground level, there is a layer of very dense sand. So most of the multi-story buildings are supported on piles embedding in this dense sand layer actually. So here, each pile is a segment of 10 meters length. It is driven with a drop hammer. Like there is a hammer of 4 tons weight, which is raised by around zero point 0.5 to 1 meter and dropped. Then what happened? There were a large number of piles to be installed, and the project was running behind the schedule actually. Then the contractor came with a suggestion. So why don't we try and speed up the driving? So he suggested, look, the upper 10, 20 meters is very soft clay. So here, normally we use a zero point 0.5 to 1 meter drop height actually. Because if you drop from a larger height, there is a possibility that piles may be damaged. So what the contractor felt, since the upper strata is very soft, why don't we use large height? Like let us use a drop height of say 2 meter, 2.5 meter. And since the soft clay, uh, since the piles are being driven through soft clay, the soil resistance is less and the piles will not be damaged actually. So, there was a meeting, the contractor came with a suggestion, and I was working for the client actually, supervising the job on behalf of the client. So it was like everyone looked towards me, like, what do I say? Like that. So, so when you look at from a common sense of point of view, that means intuitively you feel, okay, the piles are going through very soft clay. So even if you drive the pile using large drop height of hammer, nothing will happen. But fortunately for me, I had a copy of this wonderful book, like Foundation Engineering by Peck Hansen Thornburn, one of the classic books actually. So where he has described the process of pile driving. So here, like nowadays, most of us are aware about pile dynamics, but maybe this I am talking about something like 40 years ago, like that. So we did not have that kind of knowledge, particularly in India. So here, when the hammer impacts the pile, the impact travels as a stress wave down the length of the pile, actually. So it goes as a compression wave, and it says it stresses travel longitudinally as waves, actually. If the soil at the pile tip is hard, then the wave may gets reflected as a compressive wave actually. So always it is compression. But if the soil at the pile depth is very soft, that means if the resistance is too low, then the wave may reflect as a tension actually. So if the in that process, if the pile experiences tension, the pile may crack actually. So our common sense or intuitive feeling that if the soil is soft, nothing will happen to the pile is not the correct actually. In fact, it is the reverse. If the soil is dense, maybe the pile remains always in compression, it doesn't damage actually, because piles are designed for compressive stresses. But if the soil is very soft, the tension will be induced in the pile and it may damage. So I explained this, then I told I cannot accept your proposal actually. Uh, so they were a bit taken aback, actually. So they were veterans of the piling industry with many 20, 30 years of experience. And I was just a guy fresh out of college, actually. But still, uh, the science was on my side, actually, like that. So I felt it gave me a lot of satisfaction, because sometimes we decries, etc. We say that bookish knowledge is useless or theory is not correct. The practical experience is more important, like that. But here, purely based on theoretical concepts, I could shoot down a proposal by a practicing engineers, like that. So it was a very satisfying experience. And I want to discuss one project which has some interesting lessons. So here, sometimes we have embankments and constructed on soft clay, and it is common practice to use one-dimensional consolidation theory to predict the settlement section. So here, there was a project actually. It was an approach to a flyover. Like here, we can see the flyover, and here this part is the approach actually. And on both sides, there are reinforced concrete retaining walls, which retains the earth actually. And here at this location, there was soft clay. So this approach embankment settled actually. So unfortunately, somehow people were not aware, or the budget was not sufficient to carry out ground improvement. Ideally, we should have done ground improvement so that the settlements are minimized actually. But here, unfortunately, nothing was done. So around 3 years after construction, it was noticed, like considerable settlement was noticed. And in fact, it was about 300 mm. We can see here. Yeah. And here, this is actually the wider portion, the actual flyover structure portion. And this is the approach embankment made of earthen approach. And here we can clearly see, and this is actually, this line is the boundary, like the edge. So this part has settled by almost 300 mm around 3 years after construction. Then the client was a bit concerned, like why is it settling? How much more settlement may occur? Is there an issue for the stability of the structure, like that? So it was decided to carry out some investigation, and I was associated with that as a consultant. So two boreholes were drilled on both sides of the approach actually, and here we can see, like top there is some fill and clay sand. Then there is a thick, almost 12-meter thick layer of soft clay with SPTN value 2. Then after that, it is like stiff to very stiff to hard soils, then sand, etc. So here also more or less similar. Like here also we can see like a from 5.5 to 16 a layer of very soft clay. Like, so by looking at itself, we get the feeling that the settlement must have been due to the consolidation of this soft clay layer. So we the boreholes, did some consolidation test. All the data was there, and we tried a settlement calculation actually. So here I could realize there are some issues actually. See, one is like here it is the plan of the approach embankment. Like length is something like 105 meter, width is 24 meter, and there are retaining walls, reinforced concrete retaining walls on 3 sides. And the maximum height is here. So here is the maximum settlement has occurred. So we have to calculate the settlement along this edge actually. So here is one-dimensional approach valid? Here, that was one doubt. Then second is the loading. Like if you look at the approach, here the height is minimum and here the height is maximum. It's more like a triangular loading actually. Then how do we manage the stress distribution? Then another question which came to my mind is, see, the boreholes have been drilled close to this approach embankment. So the clay would have been already partially consolidated due to the stresses imposed by this approach embankment actually. So how will it affect the consolidation characteristics? See, now sometimes we learn much about the one-dimensional consolidation theory. All the textbooks speaks about that. But sometimes, like under what field conditions does one-dimensional compression occur? So this one book has explained it very nicely, like Soil Mechanics by Perloff and Barron. It's also a very old book. Now I think it's not available. But when I was doing my PhD at IIT Kanpur, this book was in the library. And when I was reading through that, I found this passage actually. So at that time, it made a very deep impression on me. So, like he explains very nicely under what field conditions we can apply one-dimensional consolidation theory. Sometimes we forget, like whether it is a footing or a raft or embankment, always we apply one-dimensional compression theory, which is not correct always actually. Okay. So in this case, where we have to calculate the settlement at the edge of the embankment, it is not clearly one-dimensional. So now the second, the how to calculate the stresses below the triangular loading actually. So like this book, Paulos and Davis has a lot of solutions actually. So it has an equation, stresses below the corner of a uniformly loaded rectangular area. Like if there is a rectangular loaded area with length L and width B, and at the depth Z below, it has got coefficients, and from this we can calculate the stresses actually. So what I decided, like we have a approach length 105, height here is 0, height here is 3.5 meter, like that. So I decided to divide it into 7 rectangular areas like that. So suppose I want to find the stress below this corner. So the loaded area 1 is, it has got a length of 105 meter and width of 24 meter and height of 0.5 meter, like that. So critical stress like that. Then loaded area 2, it's from here to here, like that. So I divided. Then using that charts, we can find the stresses below this point. Now at this center also, I wanted to calculate the settlement. So here we consider half width actually. Then get the settlement, stresses below the this rectangle of half width, then multiplied with 2, that will give the stress below this section. So then secondly, the consolidation properties. So we had about 6 undisturbed samples. Unfortunately, the sampling practices are not of very high quality actually, like because normally we have constraints of budgets actually, and we have a tendering system whereby the company with the lowest quote gets the job. So unfortunately, in many areas, in routine jobs, the quality of sampling is not that of a very high order like that. So we have to manage with what is available. So like we had 3 undisturbed samples from each borehole, then 4 samples from the upper very soft clay and 2 from the lower clay. So based on this data, these consolidation parameters were finalized. So now, earlier I posed a question like, what is the effect of the embankment loading on the consolidation properties? It is very clear, like some consolidation must have been occurred, but for the calculation of settlement, so we have to assume that the embankment was on the undisturbed soil, then calculate settlement. So we assume the soil to be normally consolidated, and the pre-consolidation pressures were taken accordingly. Like that. Then the settlements were calculated at this point 1 and point 2, like immediate settlement using elastic theory and using untrained modulus. Then because settlement here will be more because stresses are more actually. So please remember, like it is actually the situation is not one dimensional, but still we have used one dimensional theory because that is a very simple method, and going for more sophisticated methods were not uh, would have been difficult like that. So this is the total settlement. Like then we have a rigid reinforced concrete wall actually. So this is actually for if the embankment was completely flexible, we would have got the settlements. But then here it is not like that actually. There are RCC retaining walls also. So we took the average settlement like that. So average primary consolidation settlement 540 mm and average immediate settlement 90 mm like that. Then see the based on the CV data, the estimated degree of consolidation was 35%. So the average primary consolidation is 540 into 0.35. It was estimated as 180. That means the consolidation settlement at the end of 3 years. So predicted total settlement after 3 years will be the immediate plus this consolidation. So around 279. So this matches more or less reasonably with the observed settlement after 3 years. Then the client was also wanted to monitor the displacements actually. To what extent? So he was worried what happened. So about 1 year, displacement monitoring was carried out. That means the monitoring started after 3 years after construction. Then for another 1 year, it was carried out. So like both sides retaining wall, this is at the maximum. Like look at the average settlement, like near the abutment where the height is maximum, like 44 mm. Then near the middle, where the height is also moderate, it is 37. Towards the end, where the height is minimum, 10 mm like that. So a clear pattern is there, where the height is more, settlement is more. That's what we expect actually. Then on the other side, because left-hand side and right-hand side, there is a difference actually. If you look at one side, a settle more actually. Then lateral displacements, that means we're also monitored. So mostly, and look at longitudinal, like, see, ideally, like we don't expect the approach to move longitudinally like that. There is no reason for it to move, actually. But what it happened, like, it was like every month the readings used to be taken, and the almost 8 readings, this lateral displacements and longitudinal were zero actually. Only the last reading somehow some small displacements were indicated. It could be an error, possibly like that. So from the displacement monitoring, we could make some inferences. One is the lateral displacements were negligible, suggesting that there is no risk of instability or failure actually. So if there is something like a bearing capacity failure or a global failure, then we should expect more lateral displacements. Whereas here it is primarily vertical. The magnitude of settlements is related to the height of the approach embankment, which is as we expect actually, because our hypothesis is that the settlements are used to the due to the consolidation of the soft clay layer. So where the load is more, settlement should be more. Then settlement of the one side retaining wall was slightly more than the other. So here, if you look at the CC data, compression index, that one side, it has got higher CC. To some extent, this could be the reason. Then we try to predict the settlement after 4 years, actually. So again, the process was repeated, like again, like that. So it so from 3 to 4 years, during 1 year, what was the prediction? So prediction was something like 37 mm. Average observed settlement was around 35 mm like that. So that also tallies actually like that. So now we may get a feeling that, come on, we are able to predict this reasonably accurately, and we may have a feeling of satisfaction. But there is a catch, actually. I'll come to that. Then, based on this, like the monitoring, we made the following recommendations to the client. Actually. So, like there is a reasonable match between predicted and observed settlement. So, which validates the hypothesis that the observed settlement is due to the consolidation of the soft clay. Then deformation of the foundation strata predominantly vertical, like lateral displacements are negligible. Then the rate of settlement is indicated to decrease with time. So which means that's where we expect actually, if it is consolidation, like the rate of settlement should decrease with time. there is no indication of instability or bearing capacity failure. So what the client's primary concern is whether is there a safety issue? Is there a risk of failure? Or should they take some immediate action? So based on that, there was no like issue regarding stability of the retaining structures or the approach, but periodic maintenance has to be carried out actually. Otherwise, when there is a differential settlement between the structure and the approach, the right quality, like people driving on the road, they will not be very happy. Actually. So that maintenance has to be done. That's all required like that. See now, I was talking about the match between prediction and observation, and I told there is a catch here. So again, there was a very wonderful paper by Lamb. In fact, it was his Rankin lecture, which is entitled "Predictions in Soil Engineering," came out in 1973, actually. So he uh, classifies different types of prediction, like A, B, B1, C, C1, like that. A is before the event, like if we made a prediction before the approach was constructed, that would have been a class A prediction, which is very, very challenging. But what we made here was after the event. Like, so we knew that the approach had settled 300 mm. So based on that only, so naturally, what do we do? Like we sort of find like here the lamb's warning you can see, like he says, however, one must be suspicious when an author uses types even predictions to prove that any prediction technique is correct. So here what we do is, like somehow, like when we do the settlement calculation, we know that I have to match that 300 mm somehow, like that. So normally we have a lot of parameters. We have CC, we have pre-consolidation pressure, we have V0. So like we tend to fine tune the data so that the predicted value matches with the observed value, like that. So are we cheating? No, because sometimes see, as long as our the data interpretation is within reasonable limits, I feel it's okay, like that. See, otherwise we know like any prediction in geotechnical engineering is very, very difficult. People have conducted various competitions like the class A predictions. The range can be huge because soils are such complex materials, different strata, different properties, stress distribution, so many things are involved. Making an accurate class A prediction is really challenging. So here, at least we could give a meaningful conclusion to the client that nothing is wrong, like there is no risk of stability. So that way, I feel the exercise was useful and of value. It added value. Then I will come to some geotechnical design dilemmas. Like one of the fundamental tasks of a geotechnical engineer is like like he goes to the ground, he sees the ground, we see a geomaterial. So the first question we have to ask is whether it is a soil, is it a rock, or an intermediate geomaterial. That means materials which are intermediate between soil are called IGMs actually. Then if it is a soil, we ask, is it is a sand or a clay? Because sometimes it is obvious actually. So if it is a pure sand, if it is classifying as a SPSW, like we know it is a sand. And if it is a pure clay, we know it is a clay. But sometimes if a material, it consists of 60% sand and 40% fines, is it a sand or a clay? Like that. Then okay, we may classify because our standards say, okay, if the fines are more than this percentage, we classify it as a clay or a sand. But the soil, how does it behave like that? Just because we classify it as a sand, does it behave like a sand? So this is another question. Then another fundamental, the most fundamental question is like we are aware of drained and undrained. We study about this, but then where to use trained and where to use untrained? Because many practicing engineers like clarity on this. So here I'm just like for students and many practical engineers like who are not like experts in geotechnical engineering, I've just listed like what is an ideal drain. See, drained and undrained are ideal cases actually. In the drained, like volume changes can occur, the water can freely flow out or into the soil actually. So normally when the soil consolidates, water flows out. And sometimes when we do unloading, the soil heaves or swells, so water flows into the soil. Then no excess pore pressure is developed during loading, and change in total stress is equal to change in effective stress. So here, ideal undrained actually, the opposite actually, like that. So sometimes uh, very little practical guidance on, if you look at various codes, book, like it's not very clear, like where do I use drained, where do I use undrained? Like one thing was given by Peck, Hansen, Thornburg, like he says, like sands gravels with coefficients of permeability greater than about 10 power minus 4 centimeter seconds will undergo most circumstances as drained behavior, like that. And he also classifies non-plastic cohesionless silt as along with sands and gravels. Whereas like clays and plastic silts are classified as fine-grained soils, which tend to undrained behavior. Now, we have different systems of soil classification. Like if you look at Unified Soil Classification System, ISO, Indian standard, like the fine-grained soils is if the percentage fines is more than 50%, we classify it as a fine-grained soil, that is clay or silt. Whereas some other countries like New Zealand and Australia, soils with a fines content greater than 35% as classified as fine-grained soils, which I feel is more rational. And if you look at this, again, wonderful book by Mitchell and Soga, Fundamentals of Soil Behavior, they give a derivation, like sort of a mathematical derivation, and shows like if the soil contains like 1/3 fractions clay, its behavior will be like a clay. So, like New Zealand, Australian practice seems to be more scientific comparison with the other. Like, so the practical implication is like if you classify the soil as a clay, then probably its behavior is more undrained actually. Whereas if we classify it as a sand, we tend to use a drained approach actually. So the problem is something like 40 or 45% fines, it has silt and clay. As per Indian standard, we will classify it as a sand. Then does it mean we can use a drained analysis? So that is where we have to be a little bit careful. So now, in a particular field situation, how do we decide whether we can do a drained or undrained analysis? Because please remember, like fully drained or undrained are ideal cases. So which practicals will be somewhere in between. Some may be close to undrained, some may be close to drained actually. So I have listed four factors uh, which we should consider in deciding this. So one is the rate of loading or unloading, then degree of saturation, permeability soil, and length of drainage path. See, now coming rate of loading, say, like we have studied, like if it is loading rate is fast, then it may be undrained. If it is slow, it tends to be drained actually. But slow and fast is relative actually. So again, we have to consider these three aspects: degree of saturation, permeability, length of drainage path. Because if the soil is unsaturated, then there is no excess pore pressure. We can take it as drained. The response may be drained actually. That permeability, like we feel, and again, if you look at liquefaction of sands, like if the sand is very highly permeable material, but in earthquake, the loading is so fast, it becomes undrained. Actually. If you look at rate of loading, like, see, I was working in a project where the soil was very highly plastic silt. And the Geotechnical Investigation Agency, they had given the parameters as C0 and 5 they are given. Indirectly, it is assuming drained behavior. Like so, a friction angle of about 28 degrees was assumed. Then the pile capacity was calculated, but when they did the initial load test, they found that the actual capacity was much less compared to the predicted capacity. Then I happened to look at the data. Then I did another calculation. I assumed the behavior to be undrained. Like that means take the friction angle as 0 and assume a cohesion value based on the SPT n value. Then I found I could get a number which is close to the actual payload test result. So this was then I realized we have to be a little bit more careful, like in calculating the pile capacity, whether to use drained or undrained. So if you look at the rate of loading for a routine load test, I just give an example. Suppose the working load on a pile is 1000 kilonewton. Normally we apply 1.5 times. So the test load will be 1500. And the time to reach the maximum load, say like a half a day, if we assume. So the rate of loading is something like 3000 kilonewton per day. Whereas if you look at the actual structure, the load will be 1000 kilonewton, maximum applied load also 1000, and assume it takes 1 year construct the building actually. So the load will be applied over a period of 1 year. So the loading rate is something like 2.74. So if you look at during the pile load test, the loading rate is something like 1000 times faster. So what are the implications? Like if it is sand and gravel, maybe during load test and construction, it may be drained actually. In the case of silt with intermediate permeability, perhaps during the load test, it may be undrained, but during the actual construction, it may be drained possibly. Whereas clay, both during the test, load test, as well as the actual construction, it may be undrained, possibly like that. Then the length of the drainage path. So in the consolidation test, we know like we have single drainage, double drainage. So in the consolidation test, half the thickness of the sample is the drainage path. But what happens in the actual structure? Like here, uh, what is the region in which pore pressure develop excess? So we can, the stress isobar, so we can take that as the area. Like so probably we take something like 2 times width as the influence zone. This way also 2 times width will be the influence zone. So something like the half of that. So the length of the drainage path, that means the maximum distance which water has to travel, we can say roughly it is equal to the width of the foundation. Now, if you look at the 1 meter size footing and 10-meter size raft, then the time required for consolidation is something like 100 times because the time for consolidation is equal to proportional to the square of the drainage path actually. So same situation, the footing may be, we have to, depending on the science, we have to take a call. Then if it is a pile actually, so single pile, I just roughly this tentative influence zone where the pore pressures will develop. Whereas if it is a pile group, it is much larger actually. So, so whether it is a single pile or pile group, that way also count a lot. So we have to take a call considering all aspects, and it is not easy, like because straightforward we cannot say, okay, if it is a clay, I will do a undrained. If it is a sand, I will do a drained, because we have to look at various factors actually. And we know like somewhere we have both total stress versus effective stress analysis. So where to use total stress, where to use effective stress, again, we have to be very, very cautious actually. So in case of a foundation where stresses are increasing with time, so if it is a clay, we can do an undrained analysis. That will be conservative. But if it is an excavation where the effective stresses will be decreasing with time, we cannot use an undrained analysis. That will be on the unsafe side. So where here always we have to use effective stress analysis. Similarly, like a piles subjected to compressive loading. So in an undrained situation, we can use that. If it is a clay, we can do a undrained approach, actually total stress approach. Whereas if it is a like board pile retaining wall, actually, where we have to use effective stress analysis. Suppose we have a embankment on soft ground. See the compacted fill. So like where to use total stress, where to use effective, we have to only look at what happens to the effective stress with time. So on the compacted fill, when immediately after compaction, we know this will be unsaturated. So there will be negative pore pressure, there will be suction. So that means effective stress will be high. But then it will be exposed to rainfall, like water will infiltrate, it will get saturated, that suction will be lost, which means effective stresses will decrease with time. So this part, I have to always use effective stress analysis. Whereas the foundation strata, soft clay, it will consolidate due to the stresses imposed by the embankment. That means effective stresses will increase with time. So end of construction, I can use an undrained analysis. It will be conservative, actually. So these are the kind of things which a geotechnical engineer has to give thought to, like that. Because compared to like a structural analysis, like materials like concrete and steel, the parameters are straightforward. Like we can focus more on the calculation procedure, actually. Whereas in the case of soils, the behavior is so complex, actually. Like, so these are the things we have to spend time on, like instead of the calculations. So again, drained, uh, like I've listed the various factors, actually. So like in a practical situation, to evaluate all factors, it is not that easy, actually. Like sometimes what happens, like the researchers, I would say, are like surgeons, actually. So very precision work. Sometimes what happens, practicing engineers, we are like butchers, actually. Sometimes we simplify too much. Sometimes what happens, when I have a doubt, is it drained or undrained? Okay, I will say, okay, let me do both and take whichever is safer, like that. Sometimes I do that also. So this summarizes like the various, I think I've already explained. Let me. Then coming to, I talked about intermediate geomaterials. So these are a bit tricky, actually. Like in nature, we find a lot of IGM because we know rocks weather and become soils. Similarly, soils consolidate, get cement, becomes rocks, actually. So in between, a lot of materials are intermediate geomaterials, like hard soils, weak rocks. So there is a lot of confusion in this field because some authors, they give cohesive IGMs and some talk about cohesionless IGMs. Whereas if you look at the Indian standards, they treat IGM as a purely cohesive material. Like we have two, like YS 2911. So here between the SPTN values and the shear strength, we have these correlations. It assumes like a purely cohesive material. We also have another standard by the Indian Road Congress used for the design of highway projects and bridges, like that. So here also there is a table, like uh, this is the N value and the shear strength, actually. So it implies these kind of materials are purely cohesive, actually. If you look at, sometimes we have a materials known as completely weathered rock, which appearance wise, it looks like a coarse sand only. So if you have a N value of 60, as per this guidelines, it's implied that it'll have a cohesion of something like 400 kPa. But do these materials really have the kind of effective cohesion, actually? So we have to be a little bit careful in using this kind of guidelines, actually. So I was working on a project in India, like a very prestigious project. So it had the same project. There was two packages, actually, and two consultants working on that, actually. So in one package where I was the design consultant, so we were treating this IGMs, basically very hard residual soils and completely weathered rocks, etc. We were treating as a purely cohesive material, like because our guidelines say so. In the other package, they were treating it as a cohesionless soil. That means with a C0 and the phi value of 38 degrees, actually. Remember, same project, actually. And the pile design was going on, the foundation design was going on, everything approved. Nobody seemed to be worried, like, because I was a little bit, come on, what is this happening? Like, how can in one project we can, like, somebody is taking the same material as purely cohesive, and another person is treating as purely cohesionless, actually, like that. So I am doing a comparison. Like, suppose there is a like 18 meter of soil, then we have one diameter pile which is embedded like 2 meter into this intermediate geometry, which may be a really weathered rock, let us say, like that. In one case, I take this parameter like c dash is equal to 0, like phi dash is equal to 38. In other case, I use the other correlation. That means I treat it as purely cohesive, which some of the Indian guidelines give. C will be 1300. I calculate the capacity like that. So both are uh, more or less okay. Like here the pile length is something like 20 meters, actually. Not much difference. Like But if I look at 10-meter long piles, actually, like, so here what happens when we take 5, it depends on the overburden stress, actually. So now here the vertical stress are less, so naturally we expect much lower pile capacity. Whereas in this purely cohesive material, the capacity remains same because it is independent of the normal stresses. Like, so in this case, it gives much lower capacity like that. So again, when we use these guidelines, we have to be a little bit careful. So just because the guideline says you take like this, still we have to exercise caution. And sometimes what we do, I also do like that. I try by both methods. Like it is very crude because we don't know what is the truth actually. But sometimes as practicing engineers, we have to find practical solutions within a reasonable period of time. Sometimes I do this exercise, try with both methods and whichever is lower, take that actually. Then again, residual soils, like these are very tricky materials actually. See, normally the one of the basic problem is we cannot get anti-slip samples from residual soils. We have to depend on field test, and like SPT is very commonly used, and these are sometimes very dense, stiff materials. So static cone deltometer may not be feasible. Pressure meter is possible, but still not that common in India. So one fundamental dilemma is like we know the residual soils will have some effective cohesion. Like we cannot get both C dash and phi dash from in situ test because suppose we do SPT. So either we treat as a purely cohesionless material and correlate phi from the N value, or what we can do is treat it as a purely cohesive material and get C from the N value like that. But so here it is a bit difficult. So normally design of foundations, it's not a major concern because fortunately these are like either medium dense to dense or stiff to very stiff. So we get reasonable bearing capacity. So foundation design is not a big problem. Main challenge is in slope stability because in foundation design, even if some cohesion is there, we can ignore and still get a reasonable bearing capacity. But when we evaluate the stability of slopes, we know even a small cohesion has a profound influence actually. So we cannot ignore. So these kind of materials are very, very challenging, actually. And we don't know like what is the solution. Like people recommend like the parameters should be estimated from back analysis of failures, but sometimes it's not that easy. Like, let me just. So this was one incident actually. There was a reinforced soil wall collapsed actually. So it I, it was actually with the steel strips, and apparently there are walls on two sides, and they put a one single steel strip connecting the opposite wall, which is not supposed to be done. It's not a good design, but unfortunately, it was done and it failed actually. But what is interesting was there was a lot of discussion, and one expert's opinion was that the cause of failure was lack of shear connection between the panels actually. Because if you look at these panels, vertically there was no connection, so he said that was the reason for failure. And if you look at these panels, it is true there is no shear connection actually. You can see like this panel and there will be two elastomeric bearing pads, and the next panel will sit on top of these two bearing pads section. So there is no shear transfer except for maybe some small friction like that. Whereas in the case of small blocks, there is shear connector actually like that. And what is the importance of shear this shear transfer? Like we know, like the reinforced soil wall is embedded into the ground like that, and because of that embedment, it gets some benefit. Like because when we do finite element modeling, the pressure distribution, the effect of embedment, like we are very familiar with that. But in the actual design of RE walls, we don't take advantage of the embedment actually, like because it is ignored. So like if you are not taking that benefit into the design, then we cannot say that the failure must be due to that actually like that. And again, the if you want to take the beneficial effect of embedment, there must be shear transfer between the panels actually. So this must be monolithic, then only the benefits can be transferred like that. So apparently that explanation of the failure was not correct, but the story does not end there. Probably inspired by that, somebody thought, okay, the lack of shear connection between the panels was the cause of failure. Then somebody proposed like this, like we have a opening through the panels through which 25 dia rebars will be inserted, providing like a shear connection between the panels. So this actually practically it is very difficult and it may be dangerous also. Like we want the panels to be a little bit flexible so that when some differential settlement is there, it can adjust actually. Then putting a rebar like this, it's not advisable. And this was inspired by a wrong conjecture. Like somebody, okay, thought this must be the reason. Then somebody like, see, this kind of has a, like experts also have to be very careful when we give our opinions because it may influence others and lead them to a wrong path. And sometimes what happens, one of the issue with failures is because sometimes what happens, a particular type of structure fails, then we immediately we come to a hasty conclusion like, okay, this technology is not good, reinforced soil is not good, like prefabricated vertical drains don't work, or soil nailing does not work like that. Like something, a structure fails because of a poor design or construction, we should not blame it on the technology. Okay, do we have 5 more minutes? Like,
Yes, please go on.
yeah, okay. So this, I just want to share a very interesting experience. Like once I was visiting a site where boring was going on. So the rig operator, like he was not a very educated person. Like he was not a like he was this ordinary worker, like operating the rig. Then while talking, he just asked me, he is it true that the N value, the SPT N value, is equal to the SBC? So when he asked me, I was a bit taken aback because I have never heard this about this before. Maybe people who are in the geotechnical investigation industry, they may be more familiar. So I told him, I don't know. Like normally, what we do, like we calculate cohesion or friction angle from the N value, then we have the bearing capacity equations. That's the way we normally calculate it. Then later on, I just came back home. Then I started looking into this actually. So if you look at fine grain soils, like SPT2, like we have this Tersagi impact correlation and confined compressive strength. So the ratio unconfined compressive strength N by is around 12. Let us assume like the unconfined compressive strength is equal to 12 N kPa. So if we convert it to 10 per square, it becomes 1.2 N like that. So the undrained shear strength is half of that. So it becomes 0.6 N. So the bearing capacity, like if we ignore about shape factors, depth factors like CNC divided by, let us take a factor safety of 3. So it comes in. It is true. Like the safe bearing capacity is equal to the N value in here SBC is in tons per m square. Then coming to like coarse grain soil sands, it's a bit more complicated actually. We know it depends on the width, it depends on the depth like that. So I took we have this chart which is used to estimate settlement actually. So here the y-axis gives settlement in meter per unit pressure in kg per centimeter square. Here width actually. So suppose it is like 2 meter width, N value is 5 for a safe bearing pressure of uh, 1 kg per centimeter square, settlement will be 100 mm like that. But then if it is below water table, we have to double that value. That's how we calculate. So here I have made a comparison like different N value, like 200. Still, okay, N value is 5, doesn't match well, but 10 to 60, more or less, it's good. Like so, so both for clays and sands, it seems to work actually. So it was. I found this very useful actually. Like so, normally where I use is like one is sometimes the boring is going on at site. So people do okay 10 meters, then they ask, okay, this is the values we got. These are the strata. These are the values. Should we stop here? Should we continue further like that? So I use because sometimes we have to give a quick decision, like we don't have time to do any calculations. We may be somewhere in meeting or we may be traveling. So immediate answer. So I find this very useful actually. So I just estimate the column load, then assume a width of footing. Then from the side, I would have the bore log with me, field bore log. So I calculate the average N value within the influence zone, like 1 to 2 times the width of the footing. Then I use this correlation, rough SBC. Okay, so if that footing size is sufficient, okay, we can stop that. Otherwise, we'll go deeper. Like if the loads are high, SBC is low, we may have to go to pile foundation. So I instruct them, okay, you drill further like that. Then sometimes like a quick check on SPC calculations done by others. So I just, when a calculation comes, I just check this. If it is there is a drastic variation, then I look into deeper. Like I do my own calculations like that. If otherwise matches, I feel okay, this must be okay like that. So, but we should not oversimplify things actually. So, like it's not that everywhere we use this formula. For certain kind of use, it's okay like that. But we know things are much more complicated. Like bearing capacity is not a property of a soil; it depends on so many things actually. And when we design the allowable bearing pressure, we look at the allowable settlement and interference between adjacent footings. So many things we have to look. And sometimes like we are like, especially like we researchers, like we are very fond of models, and we have to work with models actually, because the reality is complex. Unless we simplify, unless we idealize, we cannot analyze, we cannot have a rational solution. Sometimes what happens, we have to make the habit of going to the site actually, because like when we sit in the design office, when we in the lab, we like sit in front of the computer terminal, we tend to sometimes have a idealized picture actually. So here I was when I was starting my career in the reinforced soil, we used to have this type of connection actually, this concrete panel with hooks embedded, then a steel bar running through it, and geogrid looped around this actually. So each panel has around 5 hooks, like you can see, like 5 hooks in a row. And when we design the hooks, we take the total load and we assume one of the assumptions is, key assumptions is, load is equally shared by the hooks actually, like that. But one day when I went to the site, then I just happened to look at a panel. Then I found this bar, this connector bar was touching only on 2 hooks actually. In the other 3, there was always some gap actually. So which means the load sharing is not equal. Then I went and looked at all the panels, like it was like that. Then we could see like, see any 2 points, we can pass a straight line actually. But if you have more than 2 points, unless they are perfectly aligned, this will not touch actually. So that was a big learning for me. Like, so the system, this was not a good design actually. Having 5 hooks in a row was not a good design, because we assume it is to be perfectly aligned, but while casting, it may get dislodged this way, move that way, like that. So, so, this needs some improvement. It was not a good design. Okay, another simple model, like sometimes we are worried about when we design reinforced well structures, we assume like effect of rain into that. So I used to have this conceptual model, like, okay, we assume, okay, nowadays we have extreme rainfall events, something like a rainfall event of something like 400 mm in rainfall. Entire thing seeps down into the soil below. We assume 50% porosity of the soil actually. So 400 mm rainfall means inside the soil, water will rise by twice that, say roughly by 800 mm or 1 meter like that. Then I used to do the analysis actually. Then I used to talk to a friend of mine who is a reinforced soil construction contractor actually. So he spends a lot of time at the site actually. So the moment I told him, he laughed like, this is not the way nature works. Like this is the water finds its way. The reason is he spends a lot of time at the site, and he has actually seen when rainfall occurs, water sometimes for a particular point, huge amount of water flows actually like that. So it's a different behavior actually. So again, we make a simplified conceptual picture, which need not be true. Always, it has to be cross-checked at the site, actually. Okay, I think there is. I'll just conclude. So, like we are familiar with the Berlin's geotechnical triangle, like that. Which, uh, like most of us are familiar with. So looking at my experience, I look at a sort of a hexagon actually. So like a geotechnical engineer, he starts out here, the formal education, maybe with undergraduate degree or master's degree or even PhD like that. Then he moves, joins a company, he gains work experience like that. In between, like there are knowledge available in the public domain, like there are conferences, seminars, research publications, which he has to track through like that. So these are all learnings actually. Then at the other end, there are code standards guidelines actually. Sometimes these are helpful, they guide us, but sometimes what happens, these are all not perfect documents actually. Sometimes they cause us problems also like that. Then there is technology like the boring investigations, testing, software analysis, all those aspects. So if we have access to this, we can do a better job. Otherwise, we have to do like many of us may not have that kind of technology because sampling, testing, etc. Then other aspect I call is the market dynamics actually. So how like is it is a quality job? There is a demand, or people want very low cost kind of things like that. So we have to work within all these constraints actually, but we try to make the maximum. Like, of course, like learnings, there is no limit. Like nobody prevents us from learning like that. Whereas technology, these kind of things are not in our control actually. So unless as a profession, as a group, we try to influence, it becomes difficult actually. So still, just to conclude, there are always opportunities. Like whether job is small, it's not a. Let's not be concerned about that. Always, uh, the most important thing is to have a fundamental understanding of the subject. Like do not follow like thumb rules or blindly. Even do not follow codes or guidelines or standards blindly like that. We all apply our own reasoning, like our own judgment, so that we do a good job. So with that, I'm sorry I've taken a bit more time. I'm sorry for that. And thank you all for the patient listening. And I'll be happy to answer any questions. Thank you. I think it's possible because in rocks also we do, but only problem is like long-term saturation, those effects. Maybe it is possible, I think, like that. I don't know whether is it about panels or blocks, because there are some blocks in which they use pins, sometimes fiberglass pins, like because normally like panels don't need, because each panel will have at least 2 layers of reinforcements actually, unless it's a very small height panel. Whereas in the case of blocks, we don't have reinforcements at every block actually. So we need a shear connection like that. So here it was sort of a total collapse. So it must have been a complete reconstruction. Sometimes what happens, the panels just come out actually, whereas the reinforced soil mass stays intact actually. So then the panels are put back and then nailed to the reinforced soil mass. That is possible. But here, if you look at the photograph, like not only the panels, a lot of soil also has collapsed actually. So this calls for a complete reconstruction. That's what I feel. But I have not I was not associated with the project, but my guess is that they should have done complete reconstruction. Yeah, because see, normally sometimes very hard strata, like we do 50 blows, then we see how much penetration, then we extrapolate that number for 300 mm penetration actually. That's what we do. So like it is true, like if we get 50, we can stop actually. But then suppose it is for 50 blows, the penetration was 100 mm. Then we extrapolate it to 300 mm. The actual in value will be 300. Sorry, 50 into 3, 150. So that's how it will be more than 50.